Okay, now. Moving on. Now, this is a little start, a little start. Now, from this, I want you to know a few notes. Maybe it's not obvious, but I want to point out is that not every sequence has a limit. Now, obviously not these 5 examples, but I can give you an easy example as 1, 2, 3, 4. The natural numbers, they do not have a limit. Okay, a limit must be a value. Okay, and this does not get closer to any value, therefore there is no limit. Okay, another example would be 0, 1, 0, 1, 0, 1, etc. Now this sequence, you may say, oh, where does it go? Where does it go? Does it have a trend? I think it does. It does have a trend. But does it get closer and closer to a certain value? I don't think so. Because it kind of jumped back and forth between 1 and 0. It doesn't get to one value indefinitely. It doesn't. Okay, therefore this sequence, it doesn't go to infinity, but it does not have a limit. Okay, so these are examples of sequences without a limit. The second note, a limit is unique. This may not be obvious, but bear in mind, although we don't study the formal definition of limit, we still have to know that you cannot have like 2 limits for one sequence. There is no such thing. The last one, when a sequence has a limit, then we call it, I call the sequence, convergent. Otherwise, I call it divergent. Convergent. Divergent. Convergent basically means that it's coming closer and closer, and divergent means it's just splash everywhere. In my mind, that's what it means. So a convergent sequence has a limit. Okay, so far, any questions? If no, we will go to the textbook first concept. A limit, the limit of a function. Okay, don't confuse these two, but they're very similar. Now, sequence limit, a lot of numbers, it has a trend. It has a future. Okay, so that is the limit. A function can also have a limit. Okay, look at this table. This is the table from the textbook. There is a function, it's a rational function. It's not difficult. We use a very simple example. Okay, now this function is weird. Why? Because it's not continuous, meaning that it's undefined at a certain point too. Now you learned this. When the denominator is equal to 0, the function is not defined. Therefore, at that point, there is no value. So here at this point, it's undefined. Meaning there is no value for y. Okay? But we can create a sequence from the left and the sequence from the right. You can see what I mean now. Sequence on the left. When x equal 1.9, what is the value of y? You can use the calculator and figure it out. Now here I can quickly write down the answer because I think everybody can do that. This value is 3.9. Okay. Now when x equal to 1.99, the value of y equals 3.99. And then the next value is 3.999. And the next value is 3.9999. So if I make x a sequence closer and closer to 2, and the value of y will also form a sequence, and you can clearly see that this sequence is going somewhere, right? Okay, this is one sequence on the left. There is another sequence on the right, similarly. This one from here, this way. 2.1, 4.1, 4.01, 4.001, and 4.0001. You can see that the values form a sequence, right? The values of y also form a sequence. And then the second sequence is also going somewhere. Okay? Now, in this case, we will say that the function, although it doesn't have a value at 2, but the function has a limit at 2, and the limit is equal to 4. Now, how do I write it? I write it in symbol. The symbol is the function f. Okay? Now, when x tends to 2, that's the condition. When x tends to 2, the limit of the function is equal to 4. Okay? I can write that. I can also write f of x out, not as f of x, but the expression of f of x. That also works the same way. When, sorry, this is not infinity, this is 2. When x tends to 2, the function's limit is equal to 4. So far, any problems? No? No. Our next job is to look at the graph of this function. The graph of this function. Now, we use the computer to plot the graph. Okay? Now, since there is no value at 2, so you can see a hollow circle here on the graph of this function. There is a hollow circle, meaning that there is no value there. But there are values everywhere else except 2. Do you see that? This function is almost complete, except at x equal to 4. Okay? Now, how can I see the value? How can I see the limit on the graph? I think it's even easier than the table. It's even easier than the table because although there is no value at 2, you can see the value of y gets closer and closer to 4. See this arrow, right? The value of y, when x tends to 2, it gets closer and closer to 2. And also on the other side, when you look at the graph from the other side, this is also tends to 4. This tends to 4. So both sides, they have a, I don't know what they have a trend. Both sides, they have a trend going to the value 4. Therefore, it's obvious. I can only say it's obvious that the limit is 4. Okay? So from the table, we can see that the limit is 4. From the graph, we can also see the limit is 4. Next page. Not next page. Oh, yes, I have already explained this. I have already explained this. Next page. The intuitive concept. Not the concept, the intuitive concept, meaning this is not the definition, not the definition. This symbol means when x tends to a value, the value of y also tends to another value, and that value L is the limit. Okay? Now, please note that when x tends to 0, it must be both directions, meaning from the left and the right. Later on, I will explain why. And also, note 2 is that the limit of the function is L. Doesn't mean the function value is equal to L. Now, this is very obvious in this example because the limit is 4, okay? The limit is 4. It doesn't mean f of 2 is 4. In fact, f of 2 is, there's no value. Okay, the limit and the function value are two separate things. You cannot expect them to be equal. Okay, now sometimes they happen to be equal, but you cannot expect them to be equal. Any questions so far? Now, as an exercise, also this is what the curriculum wants. Now, since we're learning the intuitive concept, as long as you can guess the limit from the graph, that's okay. Okay, as long as you can guess. If there is no limit, you just say there's no limit. If there is a limit, if you can tell, that's fine. We don't need a proof. Okay, we don't need a proof. A. What is the limit of h at x equal 1? Now, at x equal 1, if there is a limit. Can you guess the limit? Is Kelly here? Sorry, not Kelly, Wendy. Is Wendy here? Maybe Wendy is not here. Who is number 7? Let's ask Emily Cole. Emily, can you guess the limit for the first graph?
It's 3.
Yes, correct. Okay. And next one. Who's next? Nicole. For the second graph, for B, at x equal 1. Is there a limit? Nicole? What's your guess? There is
no limit.
One can be sure. Yes, there is no limit. Yeah, you're right. You're right. Your guess is correct. This is because if I I create a sequence from the left, you can see the value goes to 1. If I create a sequence from right, you can see the value goes to 2. And since they do not merge, they must converge to one value. Since they are different value, then no. Okay, then no. Although on the left it has a limit, on the right it has a limit, but it doesn't have a limit. On the whole, it doesn't. Okay, in this case, there is no limit. The limit does not exist. Okay, C, at x equal 1. At x equal 1. Is there a limit? Can you guess the limit? Whose turn now? Christy Lee.
Is the limit 3?
Yes, correct. Now, this you can see the limit is, they tend to 3. Now, although the value of the function is 10, but the limit does not necessarily equal to the value of the function. Okay, so limit is 3, correct. D. Whose turn now? Catherine. I'm sorry, not Catherine. Mavis.
There is no limit.
Correct. This value goes to infinity, there is no limit. Okay, as long as you think it's obvious, then it's okay. Okay, now let's study how to find limit for every different function that we know. First, the easiest one, continuous function. Now, if you look at the 4 graphs in this quick example, the first graph is called a continuous graph. The function is called a continuous function because it doesn't have a break like this. This is a break. This is a break. It doesn't have a break like this, and it doesn't have a break like this. The first function does not have any breaks like B, C, D. These functions are continuous function. It is okay? And since we have learned different types of functions, and almost, I say almost, is it almost? I think all functions we know. That includes trigonometry, log, exponential, whatever. They are all continuous, except when they are undefined. For example, like tangent function, they are undefined at 90 degrees. And at 90 degrees, it has a break like D. You see, tangent function has some breaks like this. Okay. So except at those places when they are where they are undefined, all the functions that we learn, they are all continuous, which is good. Which is good, because our next objective is to find the limit of continuous function. Now, let me show you how to do it. For continuous function, the limit and the function value are equal, like this. The limit is 3 and the function value is 3, and they're equal. It's so simple. You don't believe it. For the first example, you see, polynomial is continuous. Okay, polynomial is continuous. So the limit is equal to the function value. Yes, it's that simple. So instead of plotting the graph and then find the value from the graph, you don't have to. You just plug in the value, and that's it. You find it. As long as you know, oh, this function is continuous, and then you can just like substitution. That's it. That's why I say the technique today is not the focus. The technique is just too plain. Second one, this is also a continuous function. Although you may not know, but I tell you it is, okay? I tell you this. It's equal to substitution. Okay, next one. This exponential is continuous. Exponential is continuous. Therefore, substitution. Okay, last one. Sine, right? Sine is continuous. Therefore, substitution. Okay. It's too simple. It's almost too simple to believe. Now you turn on your camera and then you do your work. When you are done, raise your hand. Okay, now you can turn off your cameras. Did I skip Pearl? Pearl, do you mind telling me all the answers for A, B, C, D, Pearl?
A is 4.
B,
4.
4. C,
0.5.
0.5. D,
-1.
good. Good. Okay. Okay. Now, I think the first task is okay, right? Bearable. As long as you know this function is continuous at that particular point, you just substitute and then you're done. Okay. Now let's move on to functions that you are not sure if they are continuous. Now, if you're not sure, then you don't know, right? Then what do you do, right? What do you do? In that case, if you're not sure if a function is continuous, you can try these theorems. It's a lot, but they are all simple. It's a lot. The quantity is a lot, but they are very simple to apply and very simple to remember. Without proof. All these 1, 2, 3, 4, 5. Without proof. Let me present you the theorems of limits. Now, suppose there are two functions, f and g. Each one has a limit at a. Each one has a limit at a. That means x approaches to a, okay? One is m, one is n. L and m. L and m. K is a constant. These are all true. Number 1, the limit of k is k. That means a constant has a limit of itself. I think it's easy, right? It's easy. Constant has a limit of itself. Second, this function, k multiply a function is equal to, the limit is equal to k multiply the limit. You see? K multiply the function and then limit is equal to first limit and then multiply. That means the multiplication and the limit can be like in any order. Okay. Number 3, addition, subtraction can be done before or after limits, meaning the sum, the limit of the sum is the sum of limits. The difference, the limit of the difference is the difference of the limits. Moving on. 4, product. The limit of the product is the product of the limits. Okay. Number 5. Number 5 is talking about the quotient. The limit of the quotient is equal to the quotient of the limits, provided only the 5th one. There is something added. This is only true when m is not 0. Why? I think it's easy to understand. Because if this value is 0, then you're getting L over 0, and then this value is undefined, which means the calculation is false. It doesn't mean this does not exist. The original limit may exist, but if you use this method and then your value is undefined, you cannot go back. You cannot go back and blame the original limit, because the original limit may exist somehow. You just didn't find a way to find it. That just means this method does not work. In that case, we will teach you how to do that later. But anyway, if m is not 0, then you can use it any way you want, and that will always be correct. With that said, I hope you notice that in this case, L can also be 0. There is no constraints on L. It's just the denominator. Okay, and this does not I mean, this condition does not exist in 1, 2, 3, 4. It only exists in question 5, in theorem 5, okay? Now let's see how to apply it. Now it may look very silly, but bear with me, bear with me. Suppose this is the function. Suppose you don't know whether or not it's continuous. Although with my knowledge, I know it is. With my knowledge, but with your knowledge, I don't know. Maybe you think it is, maybe you don't. Maybe you're fuzzy. If you're fuzzy, then what you do is you have the sum, right? And then you separate it to the sum of the limits. Okay. And then this one, you know it's 5. And this one, if you're still not sure, you can also take out 2. If you're not sure, not necessary. I mean, if you're sure, you can already put in the value, like you did with example 1. Now with example 2, if you're not sure, then you can take out 2 and then look at the core part. If you are, oh, now you know it's, now suppose you know, oh, this is continuous, then you do the substitution. You know what I mean? Do you know what I mean? Okay, this is all like I'm just demonstrating. I'm not saying this function is so mysterious and no one knows why it's. Suppose you don't know it's continuous. Okay, this is what you can do. Another thing is, suppose you don't know, although you should know. This function is rational function. It's defined. It's continuous. Okay, it's continuous. But suppose you don't know. If you don't know, and then you can make it this way. Okay, and then since this is a straight line, this is parabola, straight line, parabola. These must be continuous. You know, okay? Then you can substitute. Okay. What I mean is you do this, you use these 5 theorems to an extent that where you can be sure that they are continuous, and then you're done. Okay, classwork. You do it, you turn on, and then you do the same thing. Raise your hand when you're done. Now, Catherine, can you tell us your answers for these 2 questions, Catherine?
9 and 4, 9 times log 3.
Okay, 9 and 9 times log 3. Okay, correct. Okay, in MEM2, you must leave your answer like that. Even though log 3 can be equal to a decimal, you still write log 3, okay? Okay, that's it. I'm just hoping that you know, oh, at least this one is continuous and this one is continuous separately. Do you know that when they are put together, they're also continuous? That is maybe a little out of reach, but with this statement, I put by myself, this sentence in red, that all functions we know. That means all the functions that you can possibly imagine in your head, although you didn't learn it at school. Maybe you can write a random function and it's always going to be continuous. So you can be quite safe when you're dealing with this. It's most of the time you can just do this substitution. Okay. That's most of the time. Okay. So far, any questions? Because continuous functions limit is one part. Okay. After this, it's all about how about not continuous, what we call discontinuous. And that's the main body of this chapter. So far, any questions about continuous functions limit? If no, let's move on. Now, starting from example 3, we are going to deal with discontinuous function. Okay. Now, what kind of discontinuous function? I can give you a preview. It's a function like this, like C, like C. In some textbooks, these kind of discontinuous, because you can see B, C, D are all discontinuous, okay? But they are different types. Now, B is one type, C is one type, and D is one type. Now, this type in some textbook is called the first type discontinuous because it's easy to fix. Later on, I will explain how to fix. It's easy to fix. So there is a continuous, but there is a limit. Sorry, there is a limit, but you cannot get it by substitution. You have to work around it. Okay, how to do that? Let me show you. First, you must identify it. How do you identify? You can do the substitution. On rough work, you can do the substitution. And then you get 0 over 0, right? You can try substitution and it doesn't work. Okay, this is like the theorem number 5 when number 5 fails. Okay, when number 5 fails, it doesn't mean the limit does not exist. It means your method is incorrect. And we have a way to go around it. And then you have to learn this way. What is this way? This way is called factorization. So it's not like, oh, something new. You can use factorization to fix it. With this type of discontinuous, you can always use factorization. Let me erase this. So this is equal to factorization. Okay. After factorization, you will get okay. And when the factors are deleted, you find that somehow the discontinuous, that point had disappeared. And then you can treat this as continuous. This is continuous. And then you can do the substitution. And then you're done. Another example. Again, you can try substitution. Okay. Sorry, this I must change. This is not 2, this is 0. This is 0. Change it a little bit. Otherwise it's continuous, you know what I mean? I'm going to change it. Now you can do the substitution. Now when you do the substitution, you will see 0 plus 1 square minus 1 divided by 2 times 0. And this is when the theorem 5 it stopped working. Okay. And then you just have to erase it and work around it using factorization. Do not expand, just factorize. Okay, and then you delete. And then you will have a function that is fine. This function is fine. This function is continuous, okay? And then you do the substitution, not infinity is 0, 0. And then 3 times 2, 6. Okay, part C. Part C also, when you do the substitution, you will see root 4 minus 2 divided by 4 minus 4. This is 0 over 0. Again, does not work. But the limit may still exist by factorization. This one is a little bit too hard for factorization because it's not polynomial. And this happens all the time. The method to go away about it, you have to make it a polynomial. So I will rationalize it. Although we always rationalize the denominator, but this time we need to rationalize the numerator just because we need to factorize, and there's no way to do that if it's not a polynomial. So in order to do that, I will multiply the conjugate . Okay, and then I will only expand the numerator . I will keep the denominator simply because I want to maintain the factorized form. Now, if you expand it, then there's no end. There's nothing you can delete anymore. You must delete x minus 4, okay? And then you will get a continuous function. When you get the continuous function, I know it's still irrational, but it doesn't matter. It doesn't matter. If it's continuous, then that's fine. And then I can substitute. Okay. So 3 examples. I show you polynomial, and then another non-polynomial, but you can still factorize if you know some technique. And it's not new technique, it's something that you learned before. And then what you did is that you delete the discontinuous, and then you get a continuous function. In reality, I mean, not in reality, in terms of graphs, what you did, if I can illustrate in front of you, it means that what you did is that you deleted this point, and then you put a point here to make it continuous. Okay, on graph, what you did is you deleted the original undefined part or something that's weird, okay? You deleted something weird, and then you put a point back to the point to fill in the hole. You get a continuous function, and then it's safe for you to plug in. Okay, if you don't understand, let me know. You can practice this technique in the classwork. And when you're done, let me know. And also turn on your webcam. Turn on your webcam. Okay, Anna, can you tell us your answer for these three questions? Anna.
-10,
-10, correct.
-1/25,
-1/25, correct.
and 6.
6, okay. Good. Good. With this, let me just quickly tell you a trick using the calculator to check your answer if it's correct. Okay. Now, if you wonder or whether or not your answer is correct, let's say for the last one, right? For this question. And then you have no answer, you have no teacher to refer to. How do you check? You can use your calculator by substituting, but not put in 9. Put in 9.01. Okay, put in 9.01, which is a very close value to 9. And use your calculator, you will get 0.01 divided by root 9.01 minus 3, okay? And the calculator will give you an answer which is 6.001, 666,204, right? And then if your answer is 6, and it's very close to this value, then maybe you can say, oh, I have confidence that this answer is correct. Okay. I hope you get it. If you don't know what I mean, let me know. Let me know. This is the way that you can guarantee your answer is correct. Moving on. Next part. Now, next part is an addition. This part is to basically to help you build up more knowledge towards continuous function. Okay, what do I mean? What do I mean? If you look through theorem 1 to 5, you can see that you are just adding, subtracting, multiplying, or dividing. Now, there are other things you can do with functions, not just these 4 operations. You still have something else. And if those things happens, you must also be able to decide whether or not the functions are still continuous. Okay, and this is called a composite function. This is a new thing, not a new thing, but a different thing that we can do with the functions. That is what we call this. Okay, this, if you say f bracket g, okay, f bracket g, that means you put g inside f as a substitution. Okay, now you've done this before, but not really, not in the formal math lesson, let me say. You've done this before, but maybe some exercise you've done it before. Now, officially, this is me teaching you for the first time. What do I mean when I put g inside f? If g is 3 minus x and f is x cubed. What do I mean? Okay, it means that where there is x, I write g. Okay, it's x cubed, I write g cubed. Okay, I write g cubed. And because g is given, I will just write this. This is a composite function, meaning I put one function inside another one. It's like a function mummy has a function baby, like that. Okay. Now, another way of composite function is the opposite, which is g bracket f. We call g of f. This is to put f inside g. In that case, I will have, where I have 3x minus 1, I will have 3f minus 1. In this case, I will have 3x cubed minus 1. You see? Now, by the method of composite functions, I can create different functions like this. If I change the order, they will give me different result. Basically, using this method, I can generate more functions. For example, you learned exponential before, right? You also learned sine, right? So what is sine of exponential? That is another function. It's a new function. It's a new type. It's not trigonometry. It's not exponential. It's a composite function, which is new. Okay, you can also do other things. The examples are unlimited. You can create your own. Okay, basically, if we learn the basic 5 types of basic functions, you can use those to create more types that are unseen in the past. Okay, anyway, now what does the composite function do? What do they do to help us understand, find the limits more? How do we find limits better? This is theorem 4.3. This is what the textbook is calling it. I think the previous one is 4.4, 4.2, but this one is 4.3. This is this thing. Now, if you read it, you can see the limit of a composite function is the function of the limit. What do I mean? I mean, the limit of f of g is f of limit of g. Okay, this also has a condition if f is continuous at m, meaning when you put m inside f, it cannot have anything undefined. If there is anything undefined happening here, then you cannot use the method. It does not necessarily mean that the limit at the beginning does not exist. The limit may still exist. If you use this method does not work, it doesn't mean the original question has a problem, maybe because the method has a problem. That's why the condition is put there. Now, let me show you. It's a lot of words to say, but let me show you examples so you know how to use it. This example. Now, this is too easy in an example, but suppose you do not know. Suppose. I know it's silly, but suppose you do not know if this function is continuous. What can you do? If you don't know, okay? Then you can, this is f. This is limit of f is f of limit. You see here f is the square root. F is the square root. The limit of f is f of limit. You can just put the limit inside the function. Okay? And then since you are sure the parabola is continuous, right? And then you are fine. You are doing the substitution. And then you get the answer. Again, I think the example is silly, okay? Perhaps you already know it's continuous because each person, their knowledge they're just different. We don't assume that everybody is on the same level with regards of the understanding of continuous. Now, if you don't know, then you can try out this way. Another example. Suppose you don't know. Suppose you don't know, and then you can do limit of exponential is equal exponential of limit. Okay. And then you can put in, since this must be continuous, so I just put in. Okay. But of course, some students already know this is continuous because this is just an exponential. It's obvious continuous. Next one. Suppose you don't know. If sine of this you don't know, then the limit of sine is the sine of limit. okay? And that's sine pi over 2 minus pi equals sine negative pi over 2. Now this value you must know it's -1, okay? And then you're done. Now, all these examples are stupid, stupid. But I want you to understand the purpose of putting this theorem there. It's supposed to be helpful. Now, somehow, because in the past, because people know this is already continuous, so they never use this ever. So they find, oh, what's the point of learning this? There is a point, a point. I think maybe you're not going to use it very often in the future, but for the first lesson, you try it. You just suppose that you don't know, okay? Suppose you don't know if this function is continuous or not. How do you get it, right? How to get it? Work on the classwork, and then let me know the answer. Now, when you are done, you raise your hand. Okay, you can put your hand down. Toby, tell us the three answers.
1/64 is 1, C is -1.
Okay, good. Good. So this is it's a very difficult concept, the composite function, but somehow the questions are not. It's not very challenging. But later on, I think in future chapters we're going to discuss this more. Okay. Now, any questions on this part? Because we have gone back and forth. We discuss continuous first, and then we discuss discontinuous. And then we go back to continuous. And then now in example 5, I'm going to talk about another discontinuous. It's like spiral learning. You just go back again. Now this is not a new type. Okay, the next example is not a new type. It's the same kind of discontinuous. Okay, it's the same type. You are going to factorize it and then figure out plug the hole and then make it continuous, and then you can substitute. Okay, it's just that these examples are harder. Not harder, just the functions are more complicated. It has square root in it. So this one. Again, you can try out. Now, girls, at first, you can never assume that, oh, this is discontinuous or this is continuous. The only way you can be sure is to try out. You can try out. Right? You try out immediately, you know, oh, the denominator 0, then discontinuous. Okay? And then you have to work out. And then you don't deal with it as continuous. You don't ever try to plug in anything. You just have to factorize. And then you factorize. Now sometimes it's very obvious. You see 2 times 3 is 6, right? So it's very, very obvious it's discontinuous. So here I'm going to, again, in order to factorize, I will multiply the conjugate. It's the same technique. Okay. To multiply, and this value is x plus 14 minus 4. That's x plus not minus 4, minus 16, sorry, minus 16, x minus 2. Okay. And this value do not expand. What you do is further factorize. So you take out 3. Please don't expand. If anyone expand, I will punish that person. Okay. And then you delete. You get a continuous function. Okay. And then you can do the substitution. Now you can say, oh, Ms. Chen, I don't know if this one is continuous. How do I know? Then you can use the composite if you really don't know. If you have trouble. And then you can say, oh, maybe this is what I do. This is very silly. I hope you feel the same. You feel, oh, this is so silly. I have to do this. Now, if you really don't know, you do this. At least you know x plus 14 is continuous, right? And then you plug in. It's 1/14. Okay. Okay. The same thing. Same thing. You plug in, and then it's done. And as long as you delete something and then the hole in the curve is made up, you just amend it. You mend it, and then you can do the substitution. I will show you more. I'll show you more. In this one, this is discontinuous. Without checking, I know because I pre-checked. If you don't believe me, you can plug in and see. It's undefined. Now, since it's undefined, it's discontinuous, I will factorize. And since there is this radical sign in the denominator and the numerator, I will have to rationalize both. In the previous example, you only rationalize one of it. But then here in this question, you rationalize both. So both is a lot. So with this, you multiply x plus 2, the conjugate. And since you did that, you also have to multiply this. Okay, but that's not enough because you also need to multiply the conjugate of the denominator. And then since you do that, you also have to multiply the same value here. Okay, so you multiply one for the denominator, one for the numerator. Okay, now you have to choose carefully which one to expand. You will expand this and this, not anything else. Anything else must be kept in the bracket. Do not mess up with it. You will choose to expand this one, which is x plus 2 minus 4, x minus 2. And then you write that one. And then with this one, you will keep that one. You will keep this one. And then you will expand this one. This one is 9 minus x minus 7, which is 2 minus x. Okay. Now these two brackets you cannot expand anymore. You must know. Otherwise, there's nothing to be eliminated. There's nothing you can do anymore. Now you will delete the factors, and then you're left with -1. Okay. And then you will get another function, and hopefully this function is continuous. Usually this one will be. If you're not sure, you know what I do? If you're not sure, then you can just put in limit inside. This is -3 plus limit x plus 7. And then I think a lot of you should know. That's why I say, oh, this part is quite silly. Unless you don't know. This is in case you don't know. Oh, sorry. I wrote it wrong. It's negative here. It's not -3, it's negative the fraction. So it's -6 over 4. It's -3 over 2. Okay. So that's my answer. Now in the future, if you have any doubt in the answer, like I said, you can put in 2.01 in the original and see if it's equal to -3 over 2 approximately. It's 4.01 minus 2 divided by 3 minus 9.01. Now you can use the calculator to check if this value is very close to your answer. And in this case, I think so. Now classwork. Turn on your webcams and then do the classwork. And when you are done, you let me know. Okay, hands down. Cassandra, can you tell me the answer for these two?
I got 6 and -3/8.
-3/8. Okay. Check your answer. Check your answer. Now let's have a summary. Now this is the first lesson. This is the first lesson. Let's have a summary before we move on. In this lesson, what you learned is the concept of limit. The concept of limit. What does that mean to say a sequence has a limit? What does it mean to say a function has a limit? Okay. Now, when you are looking for the limit of functions, not sequence, in our textbook, we do not find this. We do not guess or find the limit of a sequence. That when you are looking for a limit of a function, I mean, our ultimate goal is to find the limit of every function, right? But so far, what have we learned? Is that for continuous do the substitution. If you're not sure whether or not it's continuous, you can use one of the theorems to help you. Okay. Now, if it's discontinuous, then we've learned this type, graph C, this type. We basically use the technique of factorization and rationalization, the conjugate one, the rationalization, and then we can make amend to this discontinuous graph and make it continuous and then do the substitution. Now this method, I know that you may think every question can be solved using this method. I don't think so. No. If you look through all the examples, you can see that these functions are of certain types. They are rational functions or they are irrational with the thirds. You see the entire this notes, we don't have exponential. Now we do have exponential, but exponential is continuous. We don't have discontinuous exponential. We haven't discussed discontinuous log, and we haven't discussed discontinuous trigonometric, right? And those are for the future. Okay, but so far with rational and the radical sign, just make sure that you know what's going on, how to find the limit. Any questions? No question? Okay, let me add one more point. With graph D and B, these two are discontinuous, and since the limit does not exist for each one, so we have no plans to find B or D limits, okay? These two, we just give up, okay? There is nothing to find, there is no answer. Any questions? That's it? Then let me I will close this file. I'll close this file. Now, before we move on, let me see what we can do in the textbook. In the textbook, I think there is exercise already. Wow. Yes, exercise 4A. Now, I recommend you go through all the questions, right? Level 1, I won't ask you to do it in the homework book. Now, later on, I will assign some of the level 2 questions, okay? Now, in this textbook, this symbol means difficult, okay? This diamond symbol. It's just more, I think it's just more rationalization and factorization to do. I mean, essentially, they are still the same type functions. Okay, later on, I will assign. I will assign. Level 1, you do it yourself. We have 20 minutes. I think I can make a very quick start. But next time, I will also try to cover this part. But I want to make a quick start. So next time, I don't have to maybe linger for too long. The second lesson. Still limits of a function, but it's a different type of limits. The concept is different, meaning I'm not looking for the limit at a point, I'm looking for a limit at infinity. Now, this is the most, I think it's the most obvious if I use a graph to explain. How can a function have a limit at infinity? Now here I mean positive infinity and or negative infinity. Okay, let me just randomly show you a graph. Look at this graph. This graph at infinity, which is here, infinity, okay? It's very, very much to the right, like outside of the screen, to the infinity. The value of the function is decreasing, but is getting to a certain value. And we can see what it is. Again, this is not by proof. As long as you can guess what this value is, that's enough. And we know, all of us can guess, the value of y is getting closer and closer to 0. So we can say the limit of the function at infinity is 0. Okay. Now, how about negative infinity? For negative infinity, you need to look at the other side. This side. Okay. And again, if you can observe, then you're fine. And we can observe that this value is 0. So we say the function has a limit at negative infinity and it is equal to 0. Okay. Now in symbol, well, how do we write it? In symbol, this is how we write it. A function at infinity is equal to something and L is the limit. In this case is 0. Okay. The next one, the negative infinity, the same. You have a value and that is the limit of f of x at negative infinity is equal to L. In this case, 0. Okay. Now, I think it's almost not necessary to go through this concept using crashed. I think it's almost unnecessary to go through this concept using the table because the table is just a bunch of experiments. You experiment, from -10, what is this equal to? I'll quickly put down. And you can see the value is getting closer and closer to 0. This is one direction, one direction. This is another direction to positive infinity. It's 0.1. Okay, and this direction also. Okay, so it's not a limit at A, it's limit at infinity or in limit at negative infinity. But there is one difference. Remember when we are talking about limit, that the two sequence from this side and this side must be equal, right? Like the second type, the previous, the B graph. Now one side is getting to 1, the other side is getting to 3, and that is not okay. That is not okay. But for this one, we do allow a different value for different direction. Perhaps, this side, in this case, they are equal. In this case, they're equal, but we can allow the value of the function tends to one value, let's say 1. At positive infinity, it tends to 1. And then at negative infinity, it tends to another value, let's say 2. And that's fine. Okay. So I have a classwork for you. This classwork is creative in a way. So can you draw a graph of a function such that the limit of the graph, limit of the function at positive infinity is 2, but at negative infinity is -2? Can you imagine a function like that? Not writing the equation of the function. I'm asking you to draw a graph that looks like that. Who wants to try? This one you have to draw on my screen. I don't know if I allow people to draw on my screen though. I think I can. I do allow. Anybody can annotate. Okay. So just try. Just try. If you cannot do both, maybe you do one side, right? Who is number 19? I want to know. Who is this person? Is it Gladys? Gladys.
No, I'm number 16.
Okay, you're number 16. Then who is 19? Huh? Do I need to check? Do I need to check my Google Classroom? 19. Cindy. Is Cindy not here? Cindy, are you here? Well, Cindy is absent. Okay, she's going to watch the video then. Now, how about the next one is Melissa. Melissa, this is a challenging one. Can you try draw on my screen? Draw a function that has a limit at positive infinity, that has a limit on at the negative infinity of different values. Melissa?
How to draw on the screen. I don't know how to draw.
You don't know how to draw on the screen, fine. Is it possible that you draw on a piece of paper and show me on my camera?
Okay.
Can't see. I think your is filtered. It's filtered.
I'm sorry, I don't know how to draw it.
I don't think that's very accurate because you didn't show. I don't think that's correct. Let me try to show all of you. Let me try to show all of you. Now you need to create a function at positive infinity, it's equal to 0. At negative infinity, it's equal to -2. So you have 0, not 0, 1 and -2. So you can plot 1 and you can plot -2. So you know that at infinity, it will get there. So how to show that a function will tend to 1 at infinity? You can just do this, like this. Do you know what I mean? Now, this means that this function is getting closer and closer to 1. And at infinity, it will approaches 0. Approaches 1. So that shows at infinity, the limit is 1. Now, how about negative infinity? How do you show that? You also draw a horizontal line. Okay. And then you draw a line. In the middle, it doesn't matter. In the middle, you can draw whatever. You can draw a lot of random things in the middle. But at the negative infinity, somehow, it looks like that. Okay. So you know that, oh, this function, in the middle, you can draw like random things because it will not affect the value at infinity. But in this case, you can see at negative infinity, the value of the function approaches -2. Okay, and we do allow that. We allow that there are 2 limits at separately. Separately, not saying there are 2 limits. It's just there are different limits because at one side there is a limit, on one side there's another limit. Is that okay? Now, this is not some function that we know. It's not trigonometry. It's not trigonometry. It's not log. It's not exponential. It's not some function we know, but we can imagine there's something like that. Okay, that's the concept. Now, something we already know. But right now, I point it out to you. Obviously, look at the note. Obviously, in the past, we studied exponential function before. At that time, we told you that this graph is asymptotic to the x-axis, meaning the graph is getting closer and closer to x-axis at negative infinity, right? So we have this, that's obvious. Let me circle the condition as well. Now, if a is greater than 1, then on negative side, the negative side limit is equal to 0. Now, this is a result that you can always use without any steps. Okay. Another graph I didn't show. Another graph is going down. I didn't draw the graph, but you know the graph is getting closer and closer to 0 at positive infinity if a is between 0 and 1. So this is another thing that we know. We say that the graph, the exponential graph, is asymptotic to the x-axis, right? Therefore, the limit at infinity is equal to 0. Now, these two we use all the time. Now, in the example, you will see we use all the time. And then I assume you understand why we use it all the time, because we know 0. Obviously, this is something obviously. It's not even called a theorem. It's obviously. Theorem 4.4. This is a theorem. Okay, this one is not new. It's not something we know. This one is a kind of new, but I think it's understandable. Without proof, it's understandable. This is when we say that if this function to infinity is getting closer and closer to 0. Okay, if some function at infinity, here at positive infinity, let's use positive infinity as an example. So at positive infinity, this function is getting closer and closer to 0. Then we can draw the conclusion that the reciprocal of the function, which is 1 over f, the reciprocal Huh? How can the reciprocal be 0 as well? No. I was wrong. The condition is wrong. Please change it. Please change it. What I mean is, let's change it. Let's change it. I think I'm crazy. This is understandable. Let me repeat. Now, if a function at infinity is approaching infinity, which means increases indefinitely, which means it gets bigger and bigger without bound, which means it can get as large as possible. Okay, I say it in 3 different ways. When a function at infinity can get larger and larger, the function can increase indefinitely. Now, in simple, I write limit f is equal to infinity. It doesn't mean that limit exists. When I write limit equal infinity, means limit does not exist. Okay, I write equal to infinity, okay, as a symbol. So you know f of x will increase without bound. Then the reciprocal should decrease and should get closer and closer to 0. Okay, and we know that the reciprocal is equal to 0. I mean, the limit of the reciprocal is equal to 0. An example would be, I know this is quite abstract, but an example would be, you see, since x is increasing, if x is increasing to infinity, right? That's in the condition. X is increasing to infinity. Then the reciprocal is approaching 0. Okay, understandable. Another example will be if x squared is getting to infinity. You know what I mean? Because if x is getting to negative infinity, that means x squared is getting to positive infinity, right? Then the reciprocal should get closer and closer to 0. You know what I mean? Now, this is something that we just understand intuitively, unless you don't think it's obvious. Now, I can give you other example. Okay? For example, 2 to the power x. This is also 0. Okay? When something in the denominator is getting infinity, in this case 2 to the power x is getting infinity, then the reciprocal should approach 0. Now we are going to use this all the time as well in the later examples. So far, any questions? If no, then I think that's all for today. Now, in the future, when this chapter is finished, I will ask to check your notes. So keep your notes well organized. You hear me? Now, this is very risky for a lot of you because I've never done this before. The entire chapter 4, 5, 6, we're doing it online. I think it's more dangerous to you, really. So I want to have more control. Maybe you call me crazy, but I want to see it. Even for like in the past, maybe your reputation it was very good. You've always been a good student. I will still ask to see your notes and see if you're keeping up to it. Okay, so if I ask to see it, don't be offended. That's all. There is one question. You can leave now unless you have a question. Sophie, what do you mean?
Like for the classwork on this page, can I draw it in another way, like starting from the quadrant one? Do you mind
You
if I do it?
can come with any direction. For example, you can
Like-
go from here. Yes, it doesn't matter.
Sure, thank you.
Okay. Okay, bye-bye.